Hello everyone, my name is Giacomo Dollevedo and I'm an undergraduate student of Automation and Control Engineering at University of Campinas. I'm here to talk about my project, the development of an optical device for cerebral measurements in humans. And to start off, let's talk about why we're developing such device. The main challenge we're facing here is the kind of environment where most of neuroscience studies are bound to. If we want to study the human brain behavior on natural settings, ideally we want that to be done on natural environments, and not to restrain our subject to laboratory-only conditions. So that's the motivation of this project, to build a device that enables us to study the human brain behavior on natural environments. In order to do that, we need a technique that is non-invasive and allows for its instrumentation to be miniaturized, such as near-infrared spectroscopy. This technique is based on placing a light detector in a source over a region of interest, and we know that near-infrared light is highly scattered by biological tissue while not being as much absorbed. This makes it so that the light can penetrate deep into the tissue and be scattered back towards the surface where it can be detected. Then, by comparing the changes of light intensity over time, it is possible to calculate changes of the main absorbers on biological tissue, which are the oxy and the deoxyhemoglobin molecules. The information about the tissue hemodynamics can be used to infer brain function, for example. As I've said, this technique allows for the miniaturization of its instrumentation, but if we take a look at how most of the commercially available systems are, they're cumbersome, they are relatively expensive, and make extensive use of optical fibers. And these are all added difficulties when we want to be able to make experiments on natural settings. And finally, this leads us to our project goals, where we're aiming to address the low portability and high cost problems of a conventional system, and not only to have a more portable device, but also to make it wearable and to be remotely operable. In the end, we want this device to be easy to reproduce, because being able to build an experiment with it on an easy manner should open more room for neuroscience studies and applications. The next thing I'm going to show you is how we're going to achieve those goals. Now, I'll be going to the technical aspects of our device, how we chose its components and how they affect the overall design. Our major concerns when choosing the electronics were, of course, their cost effectiveness, their availability, and the safety of its application. As we can see here, we can break down our design into three main components: the light sources, the detectors, and the microcontroller that will control our device. For light sources, we had two options: laser diodes and LEDs. As LEDs cost way less than laser diodes and requires less power to operate, that's our choice. As for detectors, we had a few more options. We can go with avalanche photodiodes, silicon photomultipliers, or silicon photodiodes. Again, as the first two are more expensive and operate at much higher voltage than the silicon photodiodes, we are going with the SiPDs, which suits our application very well. The only downside here is that we also have to design an amplifier circuit, because its output signal is a low current in the range of a few microamps. Finally, we had to choose a microcontroller and had a bunch of options here. We've decided to go with the ESP32 because it's easy to come by, can be programmed with the Arduino language, which is a very popular and there's plenty of support material. And also it has an integrated Wi-Fi antenna, which is a plus since we wanted the final design to be remotely operable. So by putting everything together and after designing our amplifier circuit, we ended up with these guys. Here on the detection module, we have our photodiode, a hole to mount our LED, and our multi-gain amplifier circuit. All of that arranged to a single PCB as small as a coin. As for the controller board, we have a design that can connect up to 4 of these detection modules and control the time multiplexing of 2 LEDs. The next thing I'm going to show you is our first results when testing our electronics design. To begin with, we made some stability tests using optical phantoms that simulates biological tissue characteristics. The idea here is to see how the circuit will behave in long-term measurements, and if that's going to be an issue. We can see here that over the course of 2 hours, the signal had, at worst, a drift of negative 109 microvolts per minute. Now, to check if that's bad or not, we can then compare it to one of our typical measurements. Here, the recovered physiological signal, which is the heartbeat, has an amplitude of 10 millivolts, and that corresponds to less than 1% of the signal drift we had before, which means the circuitry is robust enough for long-term measurements. Now, for testing purposes, all of those measurements were done using a high-end data acquisition board, and not through our microcontroller's analog to digital converter. But, as I said before, we want everything to operate on a remotely manner, and in order to do that, we're also developing a communication interface. Here is the same kind of measurement that I showed to you on the previous slide, but this time it was done through our microcontroller board with both desired waveforms, received over Wi-Fi and displayed on our user interface. So, to sum everything up, we have a device that's able to detect physiological changes in most scenarios. It is suitable enough for long-term experiments considering our stability results. It is able to operate on a remotely manner, and it's small enough to be portable, and also it can be used as a wearable device. We're also developing a user-friendly interface to go along with it. In the end, we hope that all of these results help to support further developments of new alternatives to near-infrared spectroscopy systems, which, in fact, are already opening new directions to neuroscience studies on natural environments. If you're interested to see how this is being applied on the bigger picture, please check out Giovanni's work at measuring brain activity in natural settings with a wearable optical system. Thank you for listening. This is the end of my presentation.